Welcome to Homework Lib.
So here we can see the three cables, namely AB, AC, and AD. So these three cables, this is supporting the balloon, and the balloon exerts a vertical force of 800 newtons. So let us take this direction as 800 newtons. So there will be tension along these strings. So let's say this is T1, tension along AC, taking this as T2, and tension along AD as T3. So in order to figure these tensions, we will first figure out the unit vectors along these directions, because T1, T2, and T3, these are the magnitudes that we have considered. So for this purpose of finding the unit vectors, let us get the position coordinates. So for D, it will be 0, 0, minus 3.3. And the position coordinate for C, again we can see, along X direction we can see this is by 2.4. Along Z it is 4.2, and there is no coordinate of Y direction, so we get 4.2, 0, and 2.4. Similarly, the coordinate of B here would be minus 4.2, 0, 0. And for A, it would be 0, 5.6, and 0. So now we figure out AB cap first. So this AB cap here will be AB vector over the magnitude of AB vector. So first let's find out AB vector, then we can divide it by their magnitudes, which can be easily determined here. So AB vector will be minus 4.2 minus 0, so minus 4.2 I cap, and 0 minus 5.6 J cap, and there is no component along Z here. So this over square root of 4.2 square plus 5.6 square, and that's gonna be 7. Similarly, we find out here AC cap. So that will be C vector minus A vector. So we just subtract the relative coordinates here. So that comes up to be 4.2 I cap minus 5.6 J cap plus 2.4 K cap, and we divide it by their magnitudes. So that is 7.4 approximately. And similarly, we get AD cap as well. So that will be minus 5.6 J cap, because there is no component along X, minus 3.3 K cap, and we divide it by their magnitude, that is 6.5. And now we use the simple equation, because at this point A, since this point is at equilibrium, we can see, so the net force here, that would be relatively equal to the null vector. So four forces are here, that is T1 vector plus T2 vector plus T3 vector plus 800, this is along the positive y direction, so that will be summing up to 0. So here T1 vector, that can be found using the multiplication of this T1 with AB cap. So let's write this in the form of equation here. So T1 times AB cap, that will be minus 4.2 minus 5.6 along the J cap, and this is I cap over 7, plus T2 times AC cap, that will be 4.2 I cap minus 5.6 J cap plus 2.4 K cap divided by 6.5 or 7.4, right? Divided by 7.4. And then we add to it this T3 and multiply with AD cap, that will be minus 5.6 J cap minus 3.3 K cap divided by 6.5, and this will be added with 800 J cap, summing it to 0. So we take the I components together and equate it to 0, J components coefficient added together equate it to 0, and similarly we do for the K caps. So first for I cap, let's separate. So it will be minus 4.2 by 7 T1, and from here we separate this component. So plus 4.2 by 7.4 T2, and from here there is no I component, so this is equal to 0. That's the one equation that we get. Similarly, we separate the j components here. So minus 5.6 T1 over 7, and from here j component we separate, so minus 5.6 by 7.4 times T2 j cap, and here minus 5.6 by 6.5 T3 along j cap, so we will not mention j cap because we are going to anyways equate it to 0. That's equation 2. And for k cap, we are finally going to write down. So here we have 2.4 by 7.4, 2.4 by 7.4 T2, and then minus 3.3 by 6.5 T3, and this would be equated to 0. Okay, yeah, so we should use this 800 as well here. So we will add here 800 to this y component and then equate it to 0. So we solve these three equations. So first we can simplify them even more so that we can get rid of these fractions over here. So first one, 4.2 by 7, so minus 0.6 T1 plus 4.2 by 7.4 if we do, that will be 0.567. So we are going to take the approx value 0.6 T2 equal to 0. So roughly. So from here what we can conclude that T1 is equal to T2. Approximately this T1 will be equal to T2, and let's put this, let's find this T3 from here and let's put in this equation 2. So let us simplify this equation 3. So if we do 2.4 by 7.4, that comes out to be 0.3 T2 minus 3.3 we divide with 6.5, we get 0.51 T3, that's 0. So from here, if we figure out T2, that will be 0.51 by 0.3 T3. This will be 1.7 T3. So let's take these values of T1 and T2 and put it in equation 2 here. So let's work here only. So this 5.6 by 7, that's 0.8 T1 minus, let's write complete thing in terms of T1. So this will be, let's divide 5.6 with 7.4, we get 0.75 T1, because T2 is equal to T1 approximately, and then 5.6 by 6.5, this comes out to be 0.86 minus 0.86. Instead of T3 we are going to write T1 or T2. So here T1 is equal to 1.7 T3, so T3 would be relatively equal to 0.58. So we'll take approximate thing here, so 0.6 T1. So T3 is 0.6 T1, so we'll write here as 0.6 T1, and we add to it 800 and equate it to 0. So this equation, let's write this equation, minus 0.8 T1 we had, minus 0.75 T1 again, and then 0.86 we will multiply with 0.6, that comes out to be 0.516. So minus 0.516 T1 plus 800 is equal to 0. So solving this here, we add all the coefficients of this T1. So that comes out to be 2.06. So we'll again take the approximate 2.1 T1 is equal to 800. So that gets us the value of T1 here as 800 over 2.1. That is 381 newtons approximately and that will be relatively equal to T2, and T3 here can be obtained by multiplying zero point 0.6 with 381, so that comes out to be 228.6 228.6 newtons. So we get the value of T1 and T2 approximately equal. This was just to ease out the calculation here. So that comes out to be 381 newtons, and T3 comes out to be 228.6 newtons. So these are the tensions that we get in the cables.